Okay, gang, I want to talk a little bit in this video, if we can, about drag forces. So let's get into it here. Drag forces. And I'm going to go a little bit more detail than your book does on this topic. And actually, at the end, it's going to get a little mathy. So, let's be prepared for a little heavy-duty math. So drag forces, let's imagine that we've got an object falling through the air, or it could be an object falling through water, moving through water, but we've got this object moving through the air here. Say that's some sort of a rock. And we know that the two forces that are acting, we've got gravity downwards, and then we've got this resistive force up. Another way of thinking of a drag force is as a resistive force. So let's call that, I'll call that R. This resistive force is trying to counteract gravity, right? It's working against gravity. In other words, I could say that the net force, F net, is mg minus R, which is to say that as the resistive force gets larger and larger and larger, the net force gets smaller and smaller and smaller. And of course, you can see that if I were to drop this rock, you could imagine that as it goes faster and faster and faster through the air, this resistive force you might be able to just intuitively imagine is going to get bigger and bigger and bigger, and that turns out to be true. As the rock moves faster, the resistive force gets greater. And you can see what would happen is as that resistive force gets larger and larger, you're going to reach a point where this resistive force is equal to mg. In other words, you're going to find that there is a point where this is equal to 0, where the F net is 0. And at that case, at that point, you reach what's called terminal speed. Okay, where the object, the rock in this case, has sped up to a point where the upward force is equal to the gravitational force downward, and at that point, net force is 0, and acceleration is therefore 0, so you're at terminal speed. I think you guys should be able to understand that concept pretty easily, I hope. It's interesting, though, to break down the nature of this resistive force, right? How might you compute the resistive force? What's it equal to? What is this resistive force? And your book goes into one model. I'm actually going to introduce two different models for this resistive force. And then we're going to do a little bit of math. So, two models for the resistive force. All right, so two models for the resistive force. And the first model that I'm going to give would be a case in which the force, the resistive force, is proportional to the velocity. So that's the first one. So the resistive force is proportional to the velocity v. And so what we can say here is the resistive force R, I'm calling this is the resistive force R, is equal to negative k v, where this thing, so let's just put a box around that. This thing, the negative k here, is some constant, right? This is some constant that's allowing you to relate R and V. And I'm actually not even going to get into that constant right now. We're going to come back to this equation a little bit later, but I want to introduce the second model, which is the one your book goes into, which is where the resistive force is proportional to V squared, to the square of the velocity. And so you might represent that as the resistive force equaling negative, we'll use a different letter, I'll call it D, negative dV squared. Okay, so this would be an equation that would relate the resistive force and the velocity, and you can see here this is the key bit right here, the fact that the velocity is squared. And again, there's this d term, and that d term, similar to this term k here, is some constant that allows you to relate these two. So these are two different models, and you can find both of these models in the real world. I think this sort of linear relationship is frequently seen if you have a resistive force in water. So for instance, if you have a boat plowing through the water, there's a certain resistive force due to the water that's given by this type of equation here. And in fact, I think you guys I know that we've already done a homework problem where you had that exact situation of a boat plowing through the water, and there was this resistance force where the resistance force was proportional to V. This is more common for air drag. So the example here would be air drag. And that's actually the context in which your book gets into it. This is not uncommon when you're talking about an object falling through the air. And your book actually, I'm going to go into it because your book does, and there's some calculations that you have to do with this equation. Your book actually goes through in some detail how you would calculate D. In other words, what is D equal to? So what your book tells us is that you can calculate D as 1/2 C rho times A. And this is a complicated term, so let's break down what these various things are. Come up with a different color. Let's use maybe a green might be nice. C is that's a terrible color, green. Need a better. I think we can come up with a better green than that. Maybe this will be better. So this is the drag coefficient. C, your book calls the drag coefficient. I'm not happy with this green at all. That's a little bit better. The drag coefficient. Okay, so this would be some constant, and actually, in the problems that we'll treat this as a constant, and as it turns out, the drag coefficient can actually change slightly depending on the speed that the object moves at, or if the shape of the object changes as it moves throughout the air. That can affect the drag coefficient, but this is just going to be a given constant. Rho is the density. This is the Greek letter rho, and it's the density of the medium. Usually we're going to think about it as the air density. So this is density. And finally, A is the effective cross-sectional area. Cross-sectional area. And by effective cross-sectional area, we're talking about that area which is perpendicular to the direction of the velocity, so perpendicular to the velocity vector. So for instance, if you imagine falling through the air, if you fell in sort of straight vertical like a pencil shape, there's going to be significantly less drag than if you fall in such a way that you're exposing your entire body to the air, right? If you were like doing a belly flop as opposed to a pencil dive, there's a lot more resistance with the belly flop than the pencil dive, and that doesn't have anything to do necessarily with the density. It just has to do with the effective area that's being exposed. And so your book derives this equation. Plug in D there, and your book says that the resistive force R, I'm not sure that your book calls it R, but I'm calling it R. R equals, 1/2 C times rho times A times V squared. And so this is the equation that your book gives you that you'll have to use to do some problems. By the way, it's worth noting then, to get back to this idea of terminal speed, how would you calculate terminal speed here? Well, what would the terminal speed be? Well, let's recognize that to think about terminal speed. Terminal speed is when the acceleration is 0. In other words, this whole thing, 1/2 C rho A V squared equals mg. And so we could come up with an equation for V that will give terminal speed. So I'll call it Vt, right? It's going to be what? The square root of 2 mg divided by C rho A. So your book also kind of goes into that derivation. So this is the speed. This term right here gives the speed at which you have a case where the resistive force, right, this is the resistive force, is equal to the gravitational pull downward. In other words, there's no acceleration. So 0 acceleration. Okay, so our two forces, the upward force and the downward force, are equal. So I'm going over that quickly because it's frankly not that interesting. What I think might be a little bit more interesting is to go back to this model here, and I want to do a little bit of math based on this model that I think is interesting, and also something that we're going to see later on. Fair warning, this is going to be a little bit mathy, but let's go ahead and think about an object moving. I'll just, for simplicity's sake, we can imagine that it's some sort of a rock or a ball moving, and we've got these two forces acting. So I'll do the picture that we did before. mg is down, and I'm going to go with the linear model, the model where the force is proportional to the velocity, and just say that we'll just call this kv, negative kv. So this is the linear case. It's going to make the math a little bit simpler. And so what I can say now is ma equals mg minus kv. Right? This is now the expression for the net force. Ma is the net force, and that's equal to this downward force mg minus the upward force, which is kv in this case. And I can also come up with an expression based on this for the terminal velocity, vt. Right? Terminal velocity is when occurs when mg and kv are equal. In other words, the terminal velocity in this case is going to be mg over k. Right? What did I do there? Just to make sure that you understand where that came from, I said, all right, mg equals kv at terminal speed. So this is at terminal speed. And then, so what is that terminal speed? Well, it's mg over k. So let's remember this. I'm just gonna put some lines here just so that we can remember that relationship, because we're gonna use that in a little bit here. So what if I'm not interested, though, in where this is going to get mathy? What if I'm not interested in necessarily the relationship or how to figure out terminal speed? What if I'm interested in the relationship between velocity and time before the terminal speed? So let's investigate the relationship between velocity or speed and time before reaching terminal speed. Okay, so before reaching terminal speed. Well, I'm going to think about this equation here, and I'd like to get time in here, right? We have velocity. I'd like to get time in here, and I can remember that acceleration is defined as dv dt, right? That's our definition of acceleration. And I can sub that in and say m dv dt equals mg minus kv. Okay? So I've just substituted right here. I've put this thing here in for a there and rewritten the equation. So now we have this relationship. And now I want to play with this a little bit. So what we've got here, this is a differential equation. And I want to sort of mess around with this and see what we can get. This is going to foreshadow some stuff that we'll see later on this year. But the first thing I'm going to do is I'm going to divide all these terms by k. I'm going to divide this by k, and I'm going to divide this by k, and I'm going to divide this by k. And what we're going to get when we do that, we just said that mg over k is equal to vt, right? So now I've got, this is mg over k, so that's just vt, right? In this case, the k's are going to go away, and then I've got m over k here. So I can now say, I can simplify this now, if I move down again. I can say m over k, I'll continue over here, m over k times dv dt equals vt minus v. Okay? And now I want to solve this differential equation. So the first thing I'm going to do here is rewrite this the following way, and I'm skipping a couple steps, but I think hopefully you can follow this without too much trouble. I'm going to go ahead and say dv over v minus vt equals negative k over m dt. So I just, this is a negative right here. I don't know how clear that is. That's a negative. I don't know. I skipped a couple sort of algebraic steps, and I'm just sort of, this is kind of like combining like terms, right? So I moved these guys, I divided both sides by this, and then divided both sides by this thing, and I flip-flop these to put a negative there for reasons that will become clear later. So this is v minus vt, and this is negative k over m. So now I've got all the v's on the left-hand side, right? And so now what I can do is I can go ahead now and I can integrate this thing. So I can integrate this thing here from 0 to v, and I can integrate this from 0 to t, and then with a little bit of effort there, we can see that what are we going to get? We're going to get the natural log, and it's sort of interesting that the natural log pops out of this, but we get the natural log of vt minus v all over vt. That's the left-hand side. That's what we get over here if we integrate that thing. And that's equal to negative k over m times t. Now, I'd like to solve for the thing I'm trying to isolate here, or I'd like to isolate is v. I'd like to see how v relates to vt in this relationship. So the first thing I'm going to do is I'd like to get rid of this ln. So I'm going to do the opposite of the natural log. So I'll go ahead and rewrite this as 1, right? Vt over v is 1. So 1 minus v over vt equals e to the negative k over mt. Okay? And now I'm looking for v, so I'm just going to rearrange a little bit more, and I can see now that I'm going to get v equals vt times 1 minus e to the negative k over m times t. Okay, and that's the final result that I was looking for here. Hopefully you followed that algebra, okay? And this is a k here, negative k. Didn't mean to cut that off, negative k. And this whole thing is the exponent, right? E to the negative k over m times t. Now, this is sort of an interesting equation, and we're going to see this equation later on in the year, and I thought it might be worthwhile to look at it now. And in particular, I want to think about this exponent right here. And I want to introduce something called the time constant. So what's called the time constant, which is another important topic, and it's given its own Greek letter. This is the Greek letter tau. And the time constant, in this case, tau is I think it's T-A-U, right? Tau is T-A-U, not T-A-O. Tau. The time constant, tau, is equal, in this case, to m over k. And another way of expressing that is that this is the time when the object reaches about 63.2% of terminal velocity, of terminal speed. Okay? And so this is time constant. And where is this number coming from? Well, that's coming from 0.632 is equal to 1 minus e to the negative 1. That's where that number comes from. And so substituting that in for substituting the tau now in up here, we can rewrite this equation as, I'm running out of space. I have to move over. I can rewrite this equation now, I'll put over here, as v equals vt, terminal velocity, times 1 minus e to the negative t over tau. And what's interesting now is I can graph this. I can make a graph of this. And if I were to graph this relationship, go ahead and graph that. I can graph velocity here and time here, and it's going to be an exponential curve. So it's going to look something like this if I were to graph this. Here's terminal velocity, right? Here's Vt. And I'm going to get something that looks like this. So this is an asymptote, horizontal asymptote. And I'm going to get something that looks like this. Okay? And now the meaning of tau is this time, right, roughly there. This is tau. Where this is, right here, is 0.632 VT. It's getting cramped. When we're about 63% of the terminal speed, that's tau. So that's this is sort of a mathy treatment, and the reason I thought to go over this right now is that this kind of expression we're going to see quite a bit later on in the year, and I thought it might be worth introducing it now. Also, good to see this this sort of differential equation, work through this kind of a differential equation again. So that's a treatment of drag forces that's a little bit more intense than what your book goes into. To remember, or to remind you of what I said was given in the book, it's really just this air drag force, and really the equations that the book gives, just to remember this, is this relationship. The book gives this relationship, and then goes ahead and defines terminal speed based on that relationship as this quantity. So you may have to have some homework problems where you have to use this equation or potentially this equation. All this other mathematical mumbo-jumbo that I showed you, the book does not go into, and you won't have problems that go into this, but this sort of line of reasoning and that math should be familiar to you for later on in the year. All right, that's all for now.